Alright, hey everyone, this is Acorn's Academy. Today we are going to talk about the SN2 reaction. So, let's go ahead and get into it. Alright, so the SN2 reaction, stands for bimolecular nucleophilic substitution. Okay, the SN2 reaction is a type of substitution reaction, right? And in a substitution reaction, we can see that we are replacing one group. In this case, we're starting with this alkyl bromide here. We're replacing it with another group. Okay, so an SN2 reaction is a substitution reaction. Okay, we're going to substitute one group or atom with another group or atom. So that's the S part of SN2. The N here stands for nucleophilic. So the N indicates that this is a nucleophilic reaction. It's a nucleophilic substitution, which means we're going to be using a nucleophile. And in that case, our nucleophile is given right here. That's hydroxide. Okay. A lot of reactions are going to have nucleophilic and electrophilic versions. So we're going to start with nucleophilic substitution. We'll see electrophilic substitution down the line. And then lastly, the 2 here, the 2 is important. The 2 stands for the kinetics of the reaction. And this indicates that the reaction is bimolecular. Okay? What this means is we have 2 molecules that are simultaneously a part of the transition state of the reaction. And we will see what that looks like in just a second here. Okay, so you'll notice I'm starting with my substrate here. My substrate is this primary alkyl halide. Okay, this is primary alkyl halide. It's an alkyl bromide. And the SN2 reaction preferentially happens with unhindered substrates. Okay, unhindered substrates. So we want our reactions to have an unhindered substrate for SN2. Okay. We already covered our strong nucleophile. Right, here's a nucleophile. And we also have this molecule here, this reagent. This is DMSO. And DMSO is a solvent. It's the solvent of our reaction. Okay, so I have this little table here that I like to fill out. I like tables. You watch my videos, you'll come to realize that I quite enjoy tables. And these 4 reactions that you see at the top, these are typically among the first 4 reactions that are taught in any undergraduate level organic chemistry course. And so I'm going to be starting with SN2, and we're going to go through all of them, and then I'll make a summary video at the end that compiles, compares, contrasts all 4 of them. So we'll go ahead and start with the kinetics. We already said the kinetics are bimolecular, right? We know that. We have bimolecular kinetics. Our substrate, we said, was unhindered. Okay, so we like an unhindered substrate. Okay. Now our nucleophile slash base strength, in this case, we said this was SN2, so we have nucleophile. And our nucleophile here is strong. Okay, we're working with a strong nucleophile here. So I'll go ahead and rewrite this real quick. This is a strong nucleophile. Okay, you want to keep in mind that a nucleophile is anything that has a lot of electron density around it. So usually this will come in the form of a full formal negative or partial negative charge. So strong nucleophile is what we like here. And I can pull up some examples. Hydroxide is a good one, right? That's the one that we're using right now. You could also have something like cyanide. You could have azide and 3-. You could have another alkoxide. Like I might have like OCH3-, right? The conjugate base of methanol. So anything that is like a strong nucleophile, anything that has like, see how all these have a full formal negative charge, right? Cn-, N3-, OR-. These are strong nucleophiles. So the SN2 prefers strong nucleophiles. We also like unhindered substrate. Remember our substrate here, I'll write this down. This is just our electrophile. Okay, that's our electrophile. Okay, now stereochemistry. We'll see what this looks like in just a second. the stereochemistry here is 100% inversion. So whatever stereocenter I attack in the molecule is going to be inverted. And you can see that even though this isn't a stereocenter, I have this hydrogen here in blue as my starting material, and then I should do this. So blue hydrogen in the starting material, it's on the wedge, and then in the product, that blue hydrogen is now on the dash. So it has flipped its stereochemistry. So that's something we expect to observe in the SN2 reaction. Our solvent type, so we already said our solvent was DMSO. Getting a little bit more detailed here, this is a polar aprotic solvent. Okay, polar aprotic, meaning that it doesn't have any acidic protons. So some examples here are DMSO, DMF, acetone. DMSO is dimethyl sulfoxide. DMF is dimethyl formamide. So you could see any of these on a question concerning SN2. So polar aprotic. Okay, and then lastly, our mechanism is concerted. Concerted meaning one step. My reaction for the SN2 has one transition state. Okay, so this is what our table looks like so far. I'll fix it up in future videos to make it look a little bit nicer, but okay. So speaking of that mechanism, let's go ahead and draw that out. So here we have the same substrate, right? That same alkyl halide, bromide, and I have my hydroxide ion to the left here. And the key thing to note is that an SN2 reaction always occurs with backside attack. Okay, backside attack. Now what this means is I have my bromine here. My bromine is a leaving group. Okay, this is a leaving group. Any sort of substitution reaction requires a leaving group. Okay, and a leaving group, as you might imagine, based on the name, is any atom that leaves the main substrate and gets replaced by another atom. So here, because we don't have a bromine in our final product, we can tell that the bromine is the leaving group. Okay? So, when we have our leaving group, we want our reaction, our mechanism, for the backside attack portion, to draw our arrow, our attack arrow, 180 degrees opposite from the leaving group. Okay, so that's going to look a little something like that. Right? See how my leaving group is on this side, my arrow is on that side. Okay? And then I have to actually show the leaving group leaving. So I'm going to show it leaving like that. Okay? And that's, you know, coming off here. That's like outside of the reaction arrow. It's leaving the reaction. Okay. So now what I'm left with here is this inverted product. Okay? We see how the bromide is like facing this direction, right? Oh boy. We see how the bromide is facing this direction, and now the alcohol is facing that direction. So my product is inverted, I've done backside attack, and I've made my product. Just like that, okay? Now we said concerted, one step. This was concerted and one step. There are no other steps to the SN2 reaction. This is complete, all right? But we'll go ahead, we'll go ahead and check out the transition state here. So I'm going to go ahead and draw in this transition state. Transition state, if you don't know, is just a kind of like a snapshot in the middle of two steps. Okay, or the middle of one step, I should say. Going from one molecule to another, the transition state is the period or a very fleeting moment where all, you know, the highest point of an energy reaction. So the molecule is transitioning from reactant to product. There we go. Okay, so if I'm looking at the transition state here, I have my carbon atom. I'll go ahead and draw this in red, right? That's this carbon atom here. So that's going to be the centerpiece. And my bromine is leaving, right? We said that the bromine is a leaving group. It has left. And in the end, we see that it has this negative charge. So in the transition state, that's going to have a partial negative charge. Similarly with hydroxide, hydroxide has that negative charge there. So this is going to have a partial negative charge here. Okay, and what this is showing is that the hydroxide is adding to the carbon atom and the bromine is leaving. Okay, so this is kind of showing this one step kind of in like slow motion. All right. So I think that just about covers everything that I wanted to talk about preliminarily for the SN2 reaction. So next up, we're going to move on to the SN1 reaction. Thank you for watching.